I'm thrilled to get a chance to talk with you. In case you're interested on, who I am, I'm Kevin. I've been around for a long time. It looks like 33 years. I feel like we're just getting started. A lot of what we're doing is what we dreamed of doing years ago. I've had quite a lot of opportunities to do a variety of things at ABB, and it's been wonderful, and it's still wonderful, and to be part of an innovative, entrepreneurial, the amount of resources that we've had to do this. It's not just the Kevin show. I bring ABB with me. I'm very proud of those three letters, and I'm going to present what they've allowed me to kind of harness and harvest and provide to the industry. Some of you may have seen these videos. They're kind of a funny story. My son was getting his master's in engineering, mechanical, and he said he took a control class. And I said, well, finally, I'll be able to talk to my son. And I looked at it, I'm like, oh my, that's what you got? And they started showing me Google and videos and said, well, shoot, I can do that. So I dug up my old book that I wrote 30 years ago, I guess, and we started shooting videos. And this silly one here has got 284,000 views. I say that's a lot of lonely engineers. That's not all my mom clicking the button. And it has been fascinating. Today's talk is really a subset of that one. But there's a whole bunch of videos. And if you just type in my name, ABB, and PID, you'll get them. If you don't, you'll get some hypnotist or historian that's named Kevin Starr. And there's a book order, and at the end of this, if you can stick with us till the end, we're going to have a kind of a drawing based on selections that you make, and we'll give them out. And we're actually, believe it or not, we're getting ready to produce the 4th version of that book. So I'm kind of a one-book wonder. I started writing that book right out of college, actually. I learned all this theory stuff. I graduated in '86, and then when I got to ABB, I was given this binder. So here's the magic numbers. Plug these numbers in, and everything will be fine. I was a systems engineer in the paper industry doing installations down in the South, all over the place. And one of the customers said, you can't touch our machine unless you tell us how those numbers work. And literally that started this whole journey of linking what I learned in school with the real world and seeing if there were commonalities and practices that we could then align. And I was fortunate enough to be able to put those with the mentoring and the help of so many, and then to put it into here. And then it's just been revised and revised. And we now have training courses and training materials and tools and all kinds of fun stuff. But it really, the kernel of this stuff starts with this particular talk. And it boils down to, what in the world is all this stuff? And you may have heard these terms, Ziegler-Nichols, proportional, integral, derivative, and it's kind of daunting. And I wish I had time to see everybody on here. I don't really see anybody. I'm talking in a room by myself to 2 screens. So if you have questions or comments or concerns, in the chat window, please type them. I guess I did put my email there. Please, send me an email. And we'll do our best to answer those. The whole reason that we're kind of excited about this is it has such a dramatic impact on production quality and cost to produce for any industry. And I've had a chance to be in all of our industries and globally do this kind of stuff, from offshore oil rigs to dairy farms to mining and minerals and metals and cement and paper, pulp and paper. There are some fundamental components that transcend industry and even technology. And I found that once you understand the causality of input and output, this stuff applies to everything, even business. I've had opportunities to manage developers, even the agile development model that we developed and came up with, that we employed, could be tuned. And matter of fact, one of these videos, this tank level video, a guy in New York who was tuning a air handling system on a high rise called me and said, hey, did you know your tank level video helped me tune the air handling system at our facility? And I'm like, you're kidding me. No, I wrote a paper and we won an award. Thank you very much. I was like, well, this stuff applies way bigger than you might first recognize. Now, the world of process control, and I've been fortunate enough to be in it and have tremendous mentors and training. I can't give you everything in 50 minutes. So what I'm going to try to do is give you the high points. And hopefully it'll spark an interest. I don't want you to leave this thinking that tuning is some magic that only the elite few specialists kind of know. I know it may seem like that, but that's just because we've been doing this for a long time, and we can look at processes and we can figure things out. And that's why I want to show you some elemental truths that I wish I had known that would have accelerated my career, and hopefully that'll help. And then we have a whole bunch of stuff that I will end this. This is a technical talk, trying to transfer information that ABB is allowing us to do, and all I'm asking is you to stay until the end and maybe click a couple buttons on topics that you might find interesting. But this is not trying to sell you. I'm trying to show you some fundamental components that allow you to do this kind of cool stuff. And for whatever reason, this is what I love to do, is I love to go into a site and figure out where they're at. And we just had a big workshop, and that became one of the biggest issues in the Industrial Revolution that we're in, is the definition of normal. Where am I, and what's good look like, and how do I know when I've left that zone? There's so much in the information age today that, do you know, and I mean, that's where I'll have a question here in a minute, but we like to look at that, and since we have the collection of, I don't know, I think I last looked, we've analyzed like 1 million loops a day, and so we kind of get a baseline based on that, and we can say, oh, you're here. That's what we call a benchmark, and then we can implement corrections to reduce your variability. And there's value in that, and that's another thing that I want you to start telling us what other technical topics you would like. There's so many, and I have a list at the end, but value, and what's the big deal about taking the wiggly line from that big wiggly line to the closer wiggly line, and then what happens if you drop it down or raise it up, depending upon your speed, if you're trying to save materials, do material substitution, speed up, slow down, or whatever. So this is the essence of what we do. But what we don't do is make controls that were intended to make things worse. This is a real life picture where I got a real trip to China, and they had an example on the right that said, when we turn your controls on, our control utilization goes up, our production goes down. And they weren't very happy with us. And I was like, well, that's not what we designed. Well, that's what happens. And they would show their hand waving like a bell. And I was like, well, that was not what ABB designed. We don't sit around trying to figure out features that we can sell that don't work or make your process bad. So my point here, one of the truths is, if you have automation equipment that is off, assume it's broken. And one of our senior field engineers used to use that as an indicator, saying if it's off, there's something wrong. And it's not that it's, I've seen, if on a paper mill, if you have a sheet break and you do a wash up and your shifts are all doing stuff to get the machine back, and they may have forgotten to put dry stock on. Okay. Then the next shift comes in and like, oh, well, that was off, so I'll leave it off. And the third shift comes in and says, oh, well, it's been off for 2 shifts. I'll probably leave it off. And next thing you know, it never gets turned on again. And so that happens. And so, and I don't want you to feel bad about that, as in today's world, there's so much automation, it's sometimes hard to keep track. Now, what we found, and this is where we're going to have a polling question, and so what Chris will do is he'll pop up a screen here, I hope, that you can pick. I'm curious to you, and I'll show you what our records have found. What would you say is eating your lunch? Or if you were to ask about control loops, do you have problems with your loops being in manual? Are they out of range? Are they increasing variability? Or are they doing a good job? I kind of am interested, and you can click a button. There's not going to be a test, and I'm just interested to see if the research that we're doing, I'll show you on the next slide, matches what you guys are seeing. Chris, what's this? I always forget. This says elapsed time, so when it counts up to what, a minute, then you can kill it, or what?
We've got about 40 seconds left.
40 seconds. So this is where it's interactive. I don't want you to think this is just one. I mean, it is kind of one-sided, but I want you to be participative, and this is a way you can do that. Also, maybe so you don't fall asleep or whatever. I also want to mention a safety moment while we're going into this. Guys, if you're driving, pull over. There's nothing here that's that important that you can't watch later. And I don't know where you're at if you're in a facility, so I can't tell you if an alarm goes off. There's not. In my house, there's not one scheduled. But please look at your exits, look where you're at, and make sure you're kind of aware specifically. And then in today's world of this virus, I hope you're all taken care. All right, so can you publish these real quick?
Sure. Just a second. Hold on, I've got to save everything.
Just be okay. So loops and manual. See, that's what I'll show you the next slide. That's great. That's kind of actually that lines up. Let me show you the next. Can I close your window there? Okay, and then I'll go to the next slide. This is what we kind of have seen. You know what the half-life of a control loop is? And, PID loops are like everywhere. There's thousands of them. When I first started, if I could do 10 loops, I thought, oh, this is wonderful. If I could do that in a week. Now I think the last one our group did, we did 1,500 at one time. And we're finding that, about 50% of your loops are going to need recalibrated within 6 months. And recalibrate, it could be a bunch of things. It could be and that's where if we had a setting, I'd have you think about what can cause a loop to go bad. It's not just tuning. And when people say it's just a tuning issue, I kind of want you don't really know this stuff. It could be an actuator, it could be a valve, it could be air, it could be dirty air, it could be the valve position, it could be the raw materials, it could be the temperature outside. And then sure, it could be the tuning, but it could be the operator range that thing runs in. It could have to do with machines that are running parallel at one time and individual. And so you move in and out. And what we're seeing more and more and more is this tendency for loops being manual, which is what you're seeing. So keep that in mind is, we didn't design all this stuff to have it turned off, so why is it off? So we need to talk about that. I'm actually seeing more loops being out of range. When we first did this, it was around 15. Now it's closer to 20 to 25, which most of us have been trying to drive production, and that means getting your actuator constraints out, and so they get into the nonlinear range. And as your actuators get out of the control range, your variability goes up, which means your quality goes down. And so there's a vicious cycle here, where the frustrating thing is 30% roughly are when you turn it on, it oscillates. I can remember one customer telling me, well, the reason we like our loops to oscillate is if we have an error, I'm always guaranteed that the corrective action is 50% of the time will be in the right direction. I'm like, could you repeat that? And I'm like, well, if it's oscillating and we have a disturbance, there's a 50-50 chance that the correction is going to be in the right way. And I'm like, well, that's nuts, guys. That's not how this was designed to work. And I would say about 1 in 4 or 1 in 5 loops are okay. But that's one of the things that's challenging too, just so you don't feel, there is no standard on this is what a good loop is. Like ISA has standards for alarms and events, and MUA, ISA standards. There are standards industrially for cyber security and safety, but when you get to control loops, there's not really a standard. So that's where you have to look at each site kind of independently, but we can break them down into flows, pressures, temperatures, levels, pH, whatever, and you can get ideas on where they should be. And that's one of the tricks, is knowing what to look at and how to harvest. Now, I'll finish this on that kind of a talk. We're all about actually production quality or cost to produce. And I'll try not to give all my war stories or we'll never get done, is, I've seen this stuff manifest itself in this chain of process, actuators, transmitters, filters. I saw a guy plug in a filter and made a head box go unstable or a tank level. And it's like, they put a filter to smooth it out, but the filter changed the dynamics and it drove it into an instability, and I get called in the middle of the night. So I've seen all of these, and our team has seen all of these. And so it does take a little bit of understanding to know, I would say, the swim lanes. And that's really, and this little bit of discussion for the next 40 minutes is to kind of go through those. Okay. Process identification. That's, to me, the starting point is, maybe you could go a little, there's other starting points, but I need to know the dynamics. If I hop in a car, I kind of want to know if I step on the accelerator, is it going to take off? I'm going to drive a semi-truck, or am I driving a Porsche, or am I driving a Volkswagen? You kind of need to know so that way you can adapt. That's all of our processes have dynamics. And I like to call those dynamics unknowns or question marks. And there are different methods for identifying those question marks. There's Newton's laws of physics called first principles. I don't know if you've ever done that kind of stuff. That's not very fun, but you can do it. I do like the one where you kind of use a mass balance or an energy balance. Actually, if you watch the tank video, you can actually tune a tank based upon the volumetric calculations without doing a bump test. It's pretty cool. So that's kind of an example, but sometimes the best way is to inject energy of some sort into this. And that's where there's a whole nother, it could be a pseudo-random binary sequence, it could be a sine wave, a step wave, a square wave, an impulse. Kevin likes to bump it. And when I say bump or a test, I'm just talking about a step change. And there are things that you need to be aware of. You just don't go and bump everything. You want to make sure you bump in the right direction. I'll give you a hint about that. And that can be open or closed loop. But the point is every process, they're so common that there's like at least six, there's way more than that, but there's 6 classifications that I want to bring your attention to that you will likely see. The pure gain process really doesn't exist. I guess a light switch would be close to that. You know, it's off, then it's on. If you slow the sampling rate down enough, you can cause any process to go into that. Now, a first order process is a time constant. You know, it's a lag, which is both like your flows, your pressures. That's the one we're going to focus on today. And I will talk about some of the higher order overdamped and underdamped solutions. And then integrating processes are like tanks. And then process with dead time, that's another one. All right. Say, Chris, you may have to let me know if I'm still talking periodically. There's a network issue flopping around on my side, so I hope I'm still talking.
Yeah, we can hear you fine.
Okay. Well, I got this thing that says your proxy server needs it. And I'm like, well, let's keep going, and hopefully I can get through this. Okay. So identification, there's a couple of ways to do it. The one there's a closed loop where you change the set point, and then there's open loop where you change the actuator. And there's what you're trying to do is figure out how much mass does this input inject into the process. It's sort of like I envision a garden hose versus a fire hydrant. You know, how much oomph does a quarter turn give me? You got to kind of know that, because if you don't know that, your controller is going to have a bad day. So that's a way to calculate the change in measured value, that triangle delta, divided by the change in the actuator that caused it. That's a great way to identify kind of the magnitude or strength of your actuation effort. The other one is how long does it take for that response to settle out? How long does it take to go from when I made the change until it settles out? Now, the purists on the phone here will realize that it's an exponential, so at 4, 5, 6 time constants. I have found that I divide by 4 better than I divide by 5. And when there's noise, my eye can't really tell the difference between 4 and 5 time constants. And if I'm going to build stability into my calculations, dividing by 4 gives me a bigger number. And so that's why I pick 4. There are other methods. There's a 2/3 method you can do, and then I have those in those videos. But you have to know kind of where this thing's going to settle out. This is where knowing the type of dynamics. If it's a tank, it'll keep going and going and going. And you need to be careful because you put in an imbalance into the dynamics, and it keeps integrating that. So I don't just do a bump test and walk away. I look and watch and make sure that this thing settles out. And if it runs, if it takes off fast and comes back, I know I've got issues. When possible, I like to go and evaluate the process by hand. I like to look at the actuator, look at the valve, make sure the instrumentation. In today's environment, that may not be so easy to do, but by looking at if you bump the actuator and it doesn't move, don't tune it. It's sort of like, go fix it. It's like if you're driving your car and you turn your steering wheel and the car doesn't turn, you don't speed up. So if you can't come up with a correlation between the actuation input and the process measurement, you need to kind of go back and figure out, do I have air? I've been to places where the instrument air came unloose to the pneumatic top hat, and that actuator never moved. So I've been to places where the I to P converter was broken, or the P to I converter was broken, or the valve positioner was open and it was full of a material like cement. So you don't assume that just because you made a change that that's going to be the change. You know, it has to kind of make sense. Now, process modeling shows up when there's a difference between your estimate, which is that dotted line, and what actually happens. And I'm going to bring this back up when I get into tuning. Aggressiveness of control tuning is really related to how accurate your estimate of the model is in the first place. And there's a way to calculate all this, but right now, if the model is vastly different than your dotted line, you need to detune that loop or change your estimate. And again, those are advanced topics, but for now, we're assuming a dotted line response, and my speed of response that I'm going to try to tune this is proportional to that red dashed line. So those are the hints that I'm going to give you. In all of these, I know how much it moved this way, how much it moved, and how long it took to get there. Now, another little hint, when you first start doing bump tests, it's a little daunting. I've seen folks, and I myself included, I kept bumping in the same direction. So then next thing I know, I'm making an off-spec product. I like to try to not bump too far away from where they're running their production process. So unless you're looking for hysteresis or backlash in the valve, you kind of, if the operator says you can do a 2% bump, this allows you to go up 2, down 4, and back 2. And then that middle one gives you the best signal to noise ratio. This is kind of an art, and a lot of times I'll look at the trends and kind of see what normal actuator chains are. I like to put the loop in manual, see if it settles out. I like to do manual changes that are small until I can start seeing and predicting the results. I very rarely will do one bump. I like to do 3 to 5 until I start to be able to predict. And that's kind of how I do this. That's when you're doing them one at a time, and that's what we teach. In today's world where you have 1,000 of these, you need to pre-qualify which loops you go after, and I'll share that at the end. Now, I talked about that. This is the S-domain stuff. So for you guys that like Laplace transforms and poles and zeros, I love that stuff, but just so you know that there is mathematical equations that match all of those processes that I just showed. If you're a purist and you're in a Z transform, dead time is hard to model in the S domain, and this Pade approximation is not a bad way to approximate dead time. That's the first order. So we have used these to help identify and capture the dynamics of the process. Do you have to be an expert in Laplace transforms? No. You need to know that the process gain and the time constant is a majority of the self-regulating loops. How much did it move and how long did it take to get there? Once I know that, then I can move on. So I just shown you that there is some mathematical background here, and you can keep going into this. This is what, when I got my undergraduate, I liked this so much, I went back to Ohio State and got my master's in this stuff. So be careful what you're listening to. It could affect you for the next 25 years. Now, in a training class, I would provide this on the whiteboard. And I said, okay, I've got my controller, and I've disconnected my controller from the process. So I am just showing an error. The measured value changed, and it stayed off. Those green dots are the process variable. The straight line is the set point. If you had to explain that error signal to somebody in descriptive words, what would those descriptive words be? And this is where if you ever have an interview with me, I'll draw this out, and it really freaks people out. Oh, they changed the machine speed. I was like, no, it's just dots on a screen. It's like, what do you see? Is the measured value changed? Okay, there's a change. Well, it's staying off the set point. Okay, there's a duration. And then the last one's kind of hard. If you look at the difference between like these two dots and these two dots, that difference is the same. Where is it that the difference jumps out? It's this one, between here and here. So when you put it together, you have the rate of change, the duration, and the magnitude. And the reason I'm showing you this is this was the epiphany or the aha moment. It's like, oh, that's what a PID control does. And then that's what allowed me to start looking at the outputs of controllers and identifying the tuning. And it helps you immensely. This did for me. Whether you just take it, but there's 3 attributes. Is the present error is called the magnitude of the error. The duration of the error deals with the past as sort of a watchdog, and the rate of change is looking at the future error. And then if you look at the mathematical equations that go with that, proportional is a proportional change that is proportional to the error. The integral is integral to the duration of the error, and the derivative is this pulse that changes. And for some reason, this picture was the aha moment for me. I was like, oh, so this explains standard parallel classical. This explains that I always thought that P kind of did its thing, and I just didn't understand it. But this picture helped me realize how this stuff was built. And if you ever get a chance to do research on the original full scope pneumatic chart recorders that had bezels and nozzles and baffles, and they're works of art. They were designed this way. And that's what I thought was fascinating. So I'll go on now. It's kind of important to start to think about the interactions between the components P, I, and D. So the first aha moment was the 3 attributes of error. The next aha moment was, what's a repeat time? I used to get that. What's a reset time? What are you resetting anyways, Kevin? Because that's the integral time, and it could be in repeats. So how is time a repeat? And then proportional could be a proportional band. It could be controller gain. It could be there's a bunch of different terms. And if you guys have the Infinity, it could be S6, S7, S8, or S5, 6, and 7, whichever, or S11. The other S numbers or letters. And so I had one guy get so shook up, why don't we have standards on tuning parameters? I'm like, because there's different companies, and we all design different stuff. But you have to step back and realize the theory of operation is the same. And that's what I've done here is the repeat time the way I like to think in a standard controller is the amount of time it takes for the proportional kick to be repeated by the integral action. So you can see your original, so you have your error as a step change, your P kick happens, then you integrate that, and the reset time is how long does it take to reset that original proportional kick. That was another aha moment. So maybe you had more aha, but that was an aha moment for me. And then we actually, when we do the training class, we actually do labs where you can experience this. You can set up, and I've done this, like if I go up to a controller and I'm being asked to tune, and I don't know what it is, I'll ask them to bench test it, or today's I'll set up a Gen Con or something like that, and I'll make a little controller, and I'll induce these, and I'll watch. I'll adjust the PI, and I'll watch the output, and then I can tell the algorithm type, and then I know how to tune it. So you can bench test stuff, and it's easier now when you can do the software. But on the left-hand side, I'm showing constant proportional with different integrals. That kind of makes sense. So I've kind of got it set up so you can see how long does it take to repeat that proportional kick. It's less. And over here, I have constant integral with different proportional. See how the slope changes? This is called the standard algorithm. The parallel controller doesn't do this. And I'll explain that here in just a minute. That's one of those other light bulbs that went off. Derivative is really another interesting one. It's looking at the slope of your error, and the derivative time is a forecast into the future. You're saying, okay, based on this slope, I expect my error to be this in the future. Well, if I know my error is that in the future, I better start correcting for that error now. And that's the whole thing. But this also illustrates the problem with derivative. Now, if you go back to the history of derivative, it was designed in the pneumatic era, and you go back and look at the full scope, the early chart recorders that are beautiful works of art. Pneumatic, air, sluggish stuff, and there wasn't noise. It just was slow, and so you could kind of goose the output with derivative, and that's what it was for. Today, you have so much noise. The change in sample to sample can produce really large future errors. So what people do is the derivative gets shrunk down so small that you're predicting out. It's almost it's a double whammy. Doesn't really do anything. Or you have to put a big old filter on the measurement. Anyways, I often say D stands for disaster, so you probably shouldn't use it. I have used derivative. It's useful on higher order systems. But for this discussion, when I walk into sites, I dump the PI and D in a spreadsheet, sort all the derivatives and flag those. Hey guys, these probably have issues. And I'm usually right. So there are cases you can use that as a phase lead, kind of like a timing on an engine. If you have a stiction in a valve, you can kind of mess with it a little bit with derivative, but for the most part, and you really need a level of knowledge when to use that. And when people say, I need the derivative for that kick, I'll show what that means here in just a minute. Now, this is one area that I've seen cause a lot of consternation in the industry is the forms of the PID algorithm. and again, this is where I wish I could talk with you in person to see if you even have seen this. It used to be very clear what vendor if you had an ABB master, it was standard. If you had a Bailey Infinity, it was parallel. If you had a Mod 300, it was classical. But then what happened is when people started mixing and matching control systems, they started changing, what am I trying to say? They would toggle between modes in the setup of the controller. And I was at one site that had, or our team was at a site that had a list of controllers that the default was parallel, but somebody didn't realize that one of these parameters toggled the algorithm between parallel and standard. And so half of the controllers were default to standard, half of them were parallel. And that poor team was like, this tuning stuff is nuts. If I put this number in on these, it works. The same number on this, it explodes. So so they were very disenchanted with process control. And I was like, oh, you guys. So what I want to do here is just to kind of show you that. And if in the book, chapter 6 has a bunch of them. A lot of times if you go to the manufacturer and look, you can see one of these pictures. So you'll see something that looks like this. Parallel controllers, they literally are parallel. So here's your air. And the air has parallel paths to an output. This is kind of the original. This is how folks made them. And you can see, and so you'll either see a block diagram like this or an equation. And what I look for is the parentheses. If there's no parentheses around this, you can kind of guess your parallel. That has a big deal to do with tuning. In this case, the proportional gain is just on the air, the integral gain is just on the integral, and the derivative is just here. Now, on Infinity, they'll put a parenthesis around the whole thing, and then they have a scaling factor. And the scaling factor is used to normalize or convert the measurement into percent. And that's the other thing. When I dump tuning parameters, I'll look at that. I'll take the span, I'll take 100 divided by the span, and that's what that calibration factor is supposed to be. And 60-70% of the time, it's not. And people will use that and detune their controller. That's another red flag. So there's two for you. You can do that now. You can go look at your derivative, dump all your tuning parameters, look at derivative, and then look at your scaling factors. And if they're off, goes to the head of the class as loops to play with. This is parallel. Standard is the one that, at first glance, it looks kind of confusing. Your error comes into this controller gain, and then the output of that gets integrated on, and the output of that gets a derivative applied to it, and then they meet back up. And so in a mathematical format, what they've done is they've pulled the control gain out front, and there's nothing in front of the error. And then there's an integral time and a derivative. This particular one is called the standard format of the PID algorithm. And the reason that we tend to like this is you set the integral based upon the dynamics of the process, and then you adjust the speed of response by adjusting the control gain. Derivative is used for something else, but for the most part, if derivative 0, you just have this top part. You can see the difference. In the parallel, they're parallel paths, so you can make a parallel and standard act the same, but you have to change two numbers. I don't know if this is making any sense to everybody, but please check to see it's now not just enough to look at the manufacturer. There's usually a function setting within the PID block that allows you to pick which form of the PID you want to use. And as wonderful as that is, it can be very confusing if you don't change that or check that. It won't be a fun day for you. This is the classic. Mod 300 was Taylor Instruments, was this. And you can kind of see what they would do here is, since derivative is predicting a future error, it would take this future prediction, add it to the current error, and then PI would operate on that. Believe it or not, I like this one if I'm doing second order or higher order or loops with some sort of dead time. This works out pretty well because the derivative becomes that second pole, your integral becomes your primary pole, and your controller gain adjusts the speed. But if derivative is 0, you see that if derivative is 0, this term goes away, and you are left with the same as a standard. So if derivative is not used, standard and classical are the same, and so you may only have two different loops. But this has been a challenge in the industry, especially now that there's a hodgepodge of control systems out there, and a lot of this stuff's been installed for 30, 40 years. There's single loop controllers that you may have lost the documentation. There's DCS controllers that may have features that the default is standard, but they may have flipped it to parallel, and it can come across as extremely confusing to folks. So hopefully you can use this to maybe clear it up a little bit. And that's what I'm trying to show here is the big difference between standard and parallel. Is on standard, once you set your integral, it self-changes based upon what your proportional is. It's just the slope. On the right, on parallel, the slope doesn't change. So what happens, and that's what gets folks confused, is you have an effective integral time that gets slower as you increase your proportional gain, which is counterintuitive. It's like you increase your proportional and the reaction to get to set point is slower. Well, that's because of the way the algorithms are written. So, man, I'm going to have to speed up. That's kind of passionate about that. I've seen that hurt so many folks. And this is the S-domain equivalent of those things. So I'm just showing you these are the dynamics are in processes on the left, and then dynamics are in processes on the right, which are the controller. Now, what's beautiful about process control, at least I think it is you get to decide. You get to come up with a tuning algorithm that takes a set point change and makes one of the items on the right. And there are different algorithms, and that's why I want to kind of to get you to tune back in here, is what technique is most common in your facility for tuning loops. So could you put this one up there? So is it Ziegler-Nichols, that's the quarter wave decay, Lambda tuning or non-minimum variance, direct synthesis or pole placement, tune by feel, guess and check, or, well, the defaults are good enough. I'm just going to leave those in there. I'm curious, again, what it is. I have a bias, and I've used a lot of these. But what is it out there in your industry? Kind of interested to hear. I know what schools teach. I get to talk to colleges pretty regularly and present this stuff. So curious to what you have to say.
Still have a few more coming in here.
All right. Interesting stories. Ziegler-Nichols, they worked for Taylor Instruments, and that's a part of ABB. And I got to go to the plant in Rochester to teach a class. And it was actually, the facility was probably on the slide. And they knew I was there teaching instruments and said, you might be interested in this back room. Well, it was the original classroom lab that these two guys worked in. So I got to walk into this literally museum, and all the stuff was old, but all the original things were right there. And I was playing with the full scopes and the pneumatics, and it's pretty neat. All right, so do you have the results you can present? Tune by feel. Oh, no, I mean, and actually, believe it or not, is when I was doing that early pneumatic stuff, the knobs there was a black and white side to the knob, and there were two knobs. And literally, when you would hook up those pneumatics, there weren't numbers. You literally would start tuning them by feel, and when you got it right, the thing would stop shaking. If you were outside the kind of the resonant frequency of the control, the thing would just oscillate, and you could literally tune by feel, and it would match. So that's where the term came from, is I got to do that, where you could literally feel a control loop until you got it. In the world that we live in, where you're entering numbers, you can't really feel the number. And so there are different techniques, and I'm going to show you one that I kind of like because I use it all the time. It's called direct synthesis, or Lambda tuning is kind of got where it may have come from, wavelength tuning, but and you may call this, it's too slow. It's, I'm looking for the long run, and there are different techniques. If you want a 10% overshoot, we can help you. If you want whatever, but I like to say, when I change the set point, I want it to come up nice and smooth and come into the set point, and I don't want to oscillate. I just want it to be robust, and I don't want to get called in the middle of the night that this thing puked itself. So I want to set it up to do this. So how do I do that? The math, and that's what I was showing you, and you might want to play with this if you want. This is the closed loop transfer function, and you plug in the dynamics of your process and the dynamics of your controller, and you can solve, or your closed loop dynamic, what you want. This GCL is what you want. I'm showing it there, 1 over TCLS plus 1. And your process is, what I'm going to say, is KP over tau PS plus 1. When you run the equation, it'll spit out a controller, and that controller has the exact form of a PI algorithm. It's not magic. That's why that works. And so these are the equations. So you can write this down. Is the controller gain is 1 over KP tau ratio. The integral is equal to the process, and there's no need for a derivative. Now, in the last lecture, someone brought up that the process gain needs to be normal, and that's, again, that's a little bit tricky. Most of today's controllers operate in percent, so there's a scale factor there. It's not in gallons per minute or liters per minute or inches or whatever. It's in percent. So that means you have a scale factor. On R800XA, that's built in. On some, it's a separate variable like the Infinity. So I don't want you to freak out about that, but you usually have a scale factor. I'm assuming everything's in percent here, so that's why it's simplified. The other thing to keep in mind is your integral time. However you calculate your time constant, if it's in seconds or minutes, make sure that your integral time has the same units. Mod 300s were kind of slower, and they worked on slower processes, so their integral time was in minutes and sometimes hours. The 800XA and Infinity were faster, and so they were in seconds, and actually Bailey could be either one. So I had one guy come flying into a class, say, you caused me all this issue, and what happened is he was off by a factor of 60 because he forgot. He was in minutes, but he entered seconds. So he wanted a 1 minute, and he entered 60, so that was pretty juicy. Anyway, so those are things that you kind of learn, and you find out pretty quick when you do it wrong. But I want you to hear another thing is, you're going to make a mistake. If you haven't done this, start on a kind of conservative loop that nobody really cares about, and sharpen your teeth there. Or if you need some coaching or helping or whatever, I don't want you to start on the most critical, hey, I think we should help with those cooling rods on that nuclear facility. You know, maybe we should start on a less critical area, and you're going to work through these things. But the thing that you have to hold on to is that the theory doesn't fail. A loop doesn't work today and then it's broke tomorrow, and you say, screw this stuff, this theory doesn't work. Something changed. Something moved out of the range that controller was designed to work in. And that's what becomes fun. And it takes a while for you to get to that point where you trust that these algorithms are right. It's and they are the underlying truths. So, you know, my hat's off to the early guys at 4A and Newton and all those fellas. But in this arena, you can pick the speed of the response. So I mentioned this thing called tau ratio. It's simply a Kevinism for closed loop to open loop ratio. So if I have a 2, that means I want the closed loop response to be 2 times longer than the open loop response. If it's a 3, 3 times 4, 1, 1. You can actually have a half. You know, like if you get in your car on a cold day, you turn the heat up really fast, and then you throttle back to speed up the response. That's a leading action. So that's what I like about tau ratio tuning is you've actually calibrated your stuff so that you can adjust the tuning with a knob, which is 1 for pretty aggressive, 4 for pretty conservative. Or if you just don't know your process model, you put in a 4. If you know it, you go with 1. Or if it's like a steam loop or something, you might be able to get a 0.7 in there. And so this is showing what it looks like a 4. If you have any of me or the guys come in and do your stuff, I'll usually have a napkin or a piece of paper or something, and I'll draw this out. Because I like to know that if a standard equation, the integral stays the same, and then I adjust the speed with the control. Now today, everybody has tuning packages and, you know, auto tuners, and those are great, but they don't replace this stuff. If you don't kind of know what the calculations should be, you don't have any idea if it was wrong. And so there's a validation step. I don't mean to blow everybody away, but this is the fun theory stuff that you can actually go through and look at the different types of processes we talked about, pure gain, first order, second order, over, under, integrating. And then you have the process things down the left. And maybe we do a talk on frequency analysis, and you're looking at, you know, that's what I find really Bode plots and finding the cutoff period and the dBs per decade and what your controllable energy is. If you have a process that has cyclic parts, you need to know that. And then the standard parallel. So this one page, and we can make this presentation available for you guys if you want it. Now, I zipped through that to kind of get you to this picture. This is an image that I took 25 years ago. And on the right-hand side, you can see that was what the control room looked like. They were folded in or quartered in controllers. And actually, before this, I got to work on pneumatic controllers. And believe it or not, I got a grievance filed on me for tuning a pneumatic controller with a screwdriver because they thought I was doing something out of my swim lane, and I had a grievance filed. And this was 30 years ago. It was an air snubber it was a filter that needed tweaked, and I pulled a screwdriver, and I had a grievance filed because I was tuning a loop with a screwdriver. So, yeah, I've been around a while, and this was a great time, but it was frustrating to get to the data. You just couldn't get it. And then the middle there was the back room. We had A to D converters. It was a lot of work. And we turned this place around with the principles that I showed you here. Today, I'll just show you in the bottom, we have moved into a future that allows us to automate and build on everything we've done. And it starts with these KPIs. And I know there's a lot of folks out there that have an automated system for control loop performance, and that's wonderful. But don't get, and so does ABB, but don't get so in love with that you forget that those numbers have to make your production quality or cost to produce better. I have had opportunity, the worst I ever saw was a place that had an automatic system with automatic bump test and no knowledge of anything. And the procedure was go in, look at your things, pick the top 10 bad guys, push the auto button, take a break, and come back and hit accept. Tomorrow, if they go off the loop, they were better. That had been the practice, and this system got so out of whack, they couldn't make a product. And they were just scratching their heads, but we followed the process, Kevin. Guys, that's my point. I'm seeing that more and more and more as we get in love with there's so much that we're dealing with. In the Industrial Revolution 4.0, there's so many things with safety, cyber. It's not just loops anymore. And that picture I showed you, you didn't have networking. You didn't have to worry about hard drive space. We have to worry about all that. So the hours in a day for you to do all this, you just don't have it. So we can help with that, and that requires you to kind of know where some KPIs or key performance indicators are. When I started, I had 10 loops. It was not a big deal. Today, there could be 1,500. I can't do all that I just showed you on independent loops. I need to pre-qualify those. So 20 years ago, we came up with some patentable KPIs, and it's like we developed a fork. When was the last upgrade to a fork come out? It's still a fork. Once we hit these, it was kind of like, we're there. There's been subtle changes, but these KPIs, looking at the control, process, and signal conditioning, I really, really, really push that. We've seen guys need help with signal conditioning. If your data's garbage, you can't really optimize it. If your process is out of whack, you can't tune it. So there's a process here that we've identified. And we've had classes, and that might be an interesting tech talk, is loop management. And these are excerpts of that, and I'll usually say, what do you see? These are real data that we came in, and it's hard for folks to see this. A lot of trend packages are difficult. The one on the left is an oscillating set point. It's really not this controller's fault. The one that's feeding it's causing it. The one on the right, that's ringing like a bell, and whenever an energy comes in, it loud. And so I've had people say, what, that's not a bell. What I mean is if you went out and hit a dinner bell and you heard it, your wave pattern, if you could draw that wave pattern, it would look a lot like this screen right here. That's not what good looks like. So then what we do is we start having, what do you see? This is where I've seen a sort of maybe go backwards a little bit as an industry, is we don't realize that multiple things can fire a loop. Like if I walk in and look at the middle sections there, I may say that loop's fine. And then I walk out, it goes bananas. And then I come back in, so you need to be able to look at the trends and the persistence and realize there's multiple things that can impact a loop. And so what I'm trying to say is there are multiple things to loop tuning. What I showed you was input-output relationships, and that's very important because you know what right is supposed to do. If it does something different, it's one of these things that's screwing the pooch. It's one of these things that's sliding you off the mark. And then you can set up a corrective action for that. And these are the most common ones. We still have a questionable call because there's still stuff we're like, we've never seen. I mean, I've looked at, personally, just yesterday, we were going through this for a client, and I'm like, I've never seen that before. And I've been doing this for 30 years. And so there's still stuff happening. I'm like, well, that's fun. Let's go find it. When you know what good is supposed to look like, then it becomes, oh, that's not good. And this one I'm showing you is a final control element is FCE. That's the ISA naming convention for a final control element. So when you have a square wave in the measurement and a triangle wave in the output, you got a problem. I guarantee you go and look at the fingers or you go and look at the valve position, you'll see it go jink, jink. So what's happening is the top hat's filling up with air, but there's so much rust or gunk or whatever around the stem that the valve can't move until the pressure over, and then it goes, it steps. So you get these square waves. Now, if I quiz you, what would a tank look like? If you did this with a tank, it'd be a triangle wave on the top and a triangle wave on the bottom. So that's the kind of fun stuff that you learn. But there's also these spikes. See those? They're asymmetric spikes. They're in one direction. That's different than symmetric spikes. So this isn't normal noise. So that's a whole other issue is why is the spike just going in one direction? So those are all fun things that you get into. When people say it was just tuning, no, it's not just tuning. But what's more fun to me than the diagnostic is the fixing things. And this is the rush I want you guys to get, is on the left, we went in and the customer said, you can't, this is how this site runs. And I'm like, well, that's not how it's supposed to run. And they had no control logic. They had not tuned it. They not tuned, they never configured it. And it was a DCS. They just took the old stuff, put in the new stuff. They didn't understand Cascade, and they had never configured it. I said, let's throw some PID-cons and GEN-cons in here and wire this thing up. And it went from the way they had operated it on the left to the right. Literally, it blew their mind. They was like, we have, oh, shoot, what else can you guys do? And on the right, this one was one where there was a deadband. In the early days of DCSs, the control execution time would stall it. So they would change the input rates or the deadbands. And then they're still out there. And so this one was the measurement. That's the way it's always been. I'm like, that's not right. That's not what good looks like. So this was the tuning, but it was a setup parameter. Once we changed that, it completely changed the nature of that machine. This was one of my ones I liked the most, and I'm almost done. So we got 3 minutes. This is when if you turn a loop on and each hump gets worse, it's not going to get better until it hits a constraint. That's a pole and a right half plane, and that's bad. And we did all this tuning stuff and turned it on, and this saved the customer $1 million a month. So what I want you to see is tuning. There's a lot of positive and there's a lot of potential, and it's not magic. And I'm just showing you the very, very tip of the iceberg here, but I hope it's enough to get you excited that, wow, maybe it opens you a world of opportunity. And by the way, we have a lot more things we can do. And so I put a list of upcoming technical talks that we've got planned, and we're working out a methodology to let you know. And I appreciate all the inputs and the attendance today. Has been wonderful. If there's anything down the left-hand side, and if there's stuff that you're interested in, maybe Chris, you can send them or we'll somehow send you a calendar or an event. We just started posted on LinkedIn, but these are the topics that clients have been telling us about. Oh, Rick, that's a good one. Those are good questions. Maybe what we can do is have the questions that come in, maybe we can figure out a methodology. We're here to help you because if you make more money, you tend to buy more stuff from us, and we love that. But our passion is helping you with your production quality or your cost to produce. Loop performance on PIDs is the backbone of automation. Matter of fact, it's probably the core of automation, and all this other stuff wraps around it, APC, everything. And if that core isn't correct or you haven't analyzed it in the last 6 months, you need to. And so what we're going to do here is end it with this, a promotion, is we're about ready to release the 4th version of that book. They asked me to write another chapter. And so if you are interested in any of these items, we will do a selection randomly of 20 people out of those that select this, and we will give you a book. And if I sign it, it's like worth crazy more money. But that's what we're saying here is I'll go through them is we have formal training we can send you. We've actually put those videos, and we have a pretty cool virtual environment, and you can do that from your home. That's pretty coaching services. Like if you're like, I just don't know what to do. Well, with this remote stuff, we can help you with that. So if you're interested, click the box. I told you how to get the YouTube series, but we can send you all the links because there's a ton of, and the descriptive 4A and descriptive statistics, if you into that stuff, I like those too. So click that. We'll send you information on how to find them. We will, for those that select the button, we'll provide a complimentary benchmark on loop performance. So those things that I was going through at the end, we're so confident that we can help you. We'll put our money where our mouth is and we'll do it. And so click that. I mean, I know some people have taken us up on that again. Fine. We'll do it again. But that's one that we'll do for you. A fingerprint is a full-fledged audit where we look at plant-wide disturbance analysis. We talk to our operators. We come up with, that's a little more intense. The digital extended advisor and performance accelerators, I haven't really talked about that, but that's the latest generation of analytics that's fascinating. The loop tuning and commissioning, we're producing that today for you. In the past, there was a thought you just can't do this remotely. Well, we have a site in Mexico that commissioned us to do this remotely, and we're now a year into that contract, and they've renewed it, and we're like, you know what? It's now time to share that experience. And we just had a recent example where we saved a client using some of the remote technology. And so in the past, it wasn't possible to do this. And one of the things I've heard from our clients is they're having trouble with loop tuning and commissioning on their stock approach. In the digital realm, we can do that and help you. So we would talk to you about that. And then we're actually getting a lot more folks asking about fleet and enterprise management. How do you consolidate, all of these into a single spot? So again, this wasn't a sales thing. These are things that we're doing, and those could be, we'll have webinars to pitch those. But for you guys that have signed in and spent an hour with us, if you check the box, we'll send you the information, we'll follow up with you, and we'll get you a copy of the book for the first 20. Well, guys, I hope you can still hear me, and so I hope that was somewhat of a worthwhile. I enjoy it. I think I gave this talk 30 years ago at an ISA show, and I get as excited today as I did back then. Oh, hey, Clinton's he's got now it's an original book. If you look on the very back cover, and it has our process control learning system. The very first printing had a process control learning system on the back cover, inside back cover. That's how I can tell. And those books are kind of turning yellow, by the way. The new ones are now a little bit different, but that makes me happy. One of the guys said this was funny. The guy said, I really like your book. I said, you do? He goes, yeah, I got a desk in my office that's offset, and it's the exact height to make my desk level. Well, hopefully you'll find more use for the book than leveling your desk. And a book on a shelf is great, but doing this stuff for real is awesome. Thank you, Nina. Again, I wish I could know all of you guys. I do read your comments on the YouTube videos. I do try to respond to your emails or at least connect you. We have quite a fabric of people that do this kind of work globally and locally and in all industries. So it's not just, there's a whole team, we call it collaborative operations. And so I guess I'll end with plug in to ABB, we've got you covered.